I'll be right there. Get my coffee. Good morning, everybody. Welcome to Chem 55 again. How's everybody holding up with all this election stuff? I tell you, I'm a nervous wreck. Oh my God. God, it's 2016 all over again.
I'm just having faith that the people won't go crazy no matter who wins.
Oh yeah, no kidding, no kidding. I mean, I know exactly what you mean, and it actually was a real present fear for me the other day. I was like, wow, I've never had this feeling before in my life. Feeling like the U.S. was going to come unglued or something. How crazy is that, you know? But no, I was literally afraid.
Back to Civil War times, North versus the South, red versus blue.
Right. And you know, one of the strange things about it, as a scientist, I think about the how close the races are. And I think, well, you know, how can they be so close? You know, how can it come down to 800 votes out of a million? You know, and it's like if you do coin flips, if everybody flipped a coin and decided who to vote for, you know, on average, average, you know, they would get the same, each candidate would get the same amount of votes, right? But they would very, very rarely be as close as the presidential races are in the US. Very, just vanishingly unlikely. Like, what is going on? I normally think of it as pairwise interaction, where two humans get together, they have an exchange, right? And one human leaves that exchange an avowed Democrat, and the other human leaves that exchange an avowed Republican, and they just grow apart. But it always has to start in pairs in order for there to be that close a distribution of Democrats and Republicans in so many states. So I don't know. It's a crazy theory, I know, but it just seems odd. Anyhow, I should probably get on with things this morning, because I'm wasting everyone's time. But I just wanted to mention it because I still feel hungover from Tuesday, and it's Thursday. All right, so titrations. I'm going to assume everybody knows what a titration is, right? where you measure an amount of something by adding something else to an endpoint, right? And they did a titration on Mars. It was one of the stupidest ones I've ever heard of, but they tried to measure sulfate by precipitation of barium. And they probably have a barium selective electrode. You know, these are a little bit specialized, but it's like a pH meter but for barium. And they found that there was 1.3 plus minus 0.5% sulfate in the soil. Yay. On Mars. I don't know what that does for us. Don't eat the dirt on Mars, basically. So, my gosh, everybody's here. Good morning, everybody. So, people, you guys are getting in the homework pretty damn well, I must say. I'm very impressed. So, I think our pace is okay here. Blah, blah, blah. That's what I just said. Oh, yeah. To do this, the reaction must have a large equilibrium price. That means that it goes to completion, right? And the reaction must proceed rapidly. It goes to completion in one lifetime, one human lifetime, right? As you know, in a few seconds, right? Each increment of titrant should be completely and quickly consumed. Duh, that's what these other ones say. An analyte should be completely used up, right? So you titrate and you have to get to the end point, right? And there's typical acid-base, oxidation, complexation, and precipitation. These are all common titration modalities. You might think, oh, geez, titrations, this is stupid stuff only for students, but no, it's used in practical chemistry all the time. All kind of labs use titrations. They're really precise. They're really accurate. Much better than the instruments a lot of the time. So, you know, and there's things you can't measure with instruments. So it's a patchwork. So as an example of a titration, you could take oxalic acid, react it with permanganate, which is purple, right? And that will make a colorless set of endpoints here, right? Makes carbon dioxide, manganese 2, and water. And in the burette here, this stuff here will be dark purple probably. Right? You're going to let this dribble into this oxalic acid solution, which is clear, right? And as the permanganate drips in there, it'll be purple for a moment until it reacts with an oxalic acid and becomes colorless, right? So you keep dripping it in here, drip, 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 drip. And then at a certain point, this solution turns pink and stays pink, right? You know, or purple, whatever. It stays, it's basically pink, right? And this stuff will stay pink for, you know, forever once you reach that end, right? When there's just enough moles of this titrant to react with the moles of analyte in here, then you get this end point. And that end point tells you the number of moles of analyte in here, right? So that is the basis of titration as a measurement, right? So, so there is a theoretical thing called the equivalence point, right? And the equivalence point is when the number of moles, I know I just said that, shut up. When the equivalence point is when the number of moles of permanganate, you know, when, you know, is 2/5 of the number of moles of oxalic acid in this case, right? But you have to go a tiny bit beyond that to get to the end point, right? So So there's always a little bit of, there tends to be a little overshoot in titration, right? So the equivalence point is the ideal, the endpoint is the measured value, right? And so in this case, prior to the equivalence point, all the permanganate reacts, and so the solution is clear. The first trace of purple is the endpoint, the measured endpoint. The solution is, it's not fucking colorless. It's fucking purple. This guy's fucked this up so bad. Anyway, I'm glad I didn't do it. The solution is just purple, right? Just barely purple. And after the equivalence point, purple is there, right? Yeah. So that they're not quite the same, right? So the equivalence point is likely a little bit before the end point, right? So so you can detect it with color or potential in an electrode or absorption. And if you do it by color, a lot of times you use an indicator. Not in permanganate, because permanganate itself is colored, but for acid base, you use phenolphthalein or something like that. So the titration error, to which I alluded to just a second ago, is the difference between the endpoint and the equivalence point. And you can estimate that by doing a blank titration, right? And the blank titration, basically you carry out the same titration, but on a solution without the analyte, right? So basically you just put in a drop, and if the number of drops that it takes to get it to the color that you say, oh, this is the end point, right? That volume is the blank volume. You can subtract that from others. It's actually not a very common practice, but you can totally do it. It should improve your accuracy a little bit. Okay. You got it. You need good standards. You guys know this stuff. And the purity can be, there are a few chemicals that are primary standard grade. It means they're just real pure. Reagent grade meets the ACS requirements for reagent gradeness, and then trace metal grade have probably lower parts per million of trace metals. But, primary standard is supposed to be 100 plus minus 1. I have not really encountered this very much in my work, but occasionally you want to be super. All right. So standardization. So mostly when you do a titration, you start by standardizing something. Okay? And so if you don't have primary standard HCl, for example, you have to standardize your base with something else. So a lot of times you use potassium hydrogen phthalate. That's an acid you can weigh out really accurately. And then you standardize the base, and you titrate the acid with the standard base. So the problem with the acid base thing is that base solutions tend to be unstable because they absorb carbon dioxide from the air, and then that reduces their base strength. And because carbonic acid is created, CO2 is created, whatever. And also glass tends to be etched by bases. So if it's like 1 molar base, it will slowly make silicates that dissolve away in the glass and then dissolve glass, as well as use up some of the acid strength. So let's just skip this nonsense, huh? Let's jump right in here. The idea is to relate the moles of titrant to the moles of the analyte. Millimoles per mil is the same as moles per liter. You need to know the stoichiometry of the reaction. For example, the calcium oxalate can be done here. You can determine the calcium content of urine. Oh, lovely example, Mr. Harris. For our first experiment, we will be measuring the calcium content of pee. Okay, so I never got out of third grade. Sue me. The calcium content can be determined by reacting the calcium with oxalate, which will form a solid precipitate here, right? This is a solute, right? And that solid, then you can filter it out. You can wash it with ice cold water, whatever. That way you you can make PT. No, just don't do that. So ice cold water to remove the free oxalate and dissolve the solid. Okay. First, you precipitate with cold water, and then first you filter and wash, and then you dissolve the solid in acid, and you get calcium 2 plus oxalate, right? So now you have your oxalic acid back, right? Then you heat it up a little bit, and you react it with standardized potassium permanganate until it's purple, right? So the first step here is standardization. And in a standardization, you're going to take a known amount of sodium oxalate, right? So this is going to be your analyte next, but at this point it's your known, and the permanganate is the analyte. So you flip the script here, start with a known amount of oxalate, react it with your unknown permanganate. And from this, you get the molarity of the permanganate solution, right? So in order to do this, you take the number of grams of oxalate, turn that into the moles of oxalate, divided by the volume of solution. You don't actually have to do this, but that will give you the molarity of the oxalic acid solution. Then you take 10 milliliters of this. Oops, actually it did say 10 mils, right? Yeah, so you do need this molarity, right? You take 10 mils of this, and that will give you this many moles. This is the molarity times 10 mils. Oops. This times this gives this, right? That's the number of moles, right? And then you multiply it by the mole ratio, right? 2 permanganates for every 5 oxalates, right? That comes back to, no, it's not there. It's way back there. It's 2 permanganates per every 5 oxalates. That gives you the number of moles of permanganate, right, or millimoles, as the case may be, right? Then you take the millimoles of permanganate divided by the volume in mils. That gives you the molarity of the permanganate, right? And this is 4 sig figs because they used 10.00 mils here, and the titrant volume was 48.36 mils, right? So this can all be carried through with a maximum of about 4 sig figs. So that's pretty darn good. I mean, it's about 1 part per 1,000, right, in terms of a random error. So sometimes instruments, when they're working well, will do that, but not all the time, you know? So this is a very precise and accurate way of doing stuff. Okay. So now, calcium in a 5 ml urine sample is precipitated with oxalate, isolated and resolved in acid. So the sample then required 16 mils of standard permanganate. Well, let's find the concentration of calcium in that solution. So this guy here, let's just let me launch ahead and try to do this one on paper here, because I don't know, maybe seeing it on paper will help, or kind of give a little bit of break to the monotony of this lecture. So, and for a change from monotony, we will be looking at a blank piece of paper. That is a Monty Python attempted reference. So, so if we have 5 millimoles, I'm sorry, 5 milliliters of urine, and when we precipitate it with oxalate, C2O4 minus 2, there we go, it's a little bit better. Then we collect it, we wash it, we dissolve it in acid, and then we titrate it, and we get 16.17 milliliters of MnO4 minus solution, right? And our goal here is to determine the amount of calcium in this urine sample, right? So first of all, let's determine the amount of oxalate, right? So that is going to be, we're going to start with the permanganate, 16.17 mils of permanganate. Then we're going to multiply that by the molarity, which is 8.792 times 10 to the minus 4 moles per liter. Divide that by then we're going to convert it to moles per mils here, right? Or take out the mils here, right? And then we'll multiply this by the stoichiometric ratio. 5 oxalates for every 2 permanganates. And this will give us the number of moles of oxalate. Right? So it's going to be mils of this times moles of permanganate per liter, right? And then times 5/2. This will give us the moles, actually the moles per liter, right, of oxalate, right? And we're going to multiply that by the stoichiometric ratio, 1 calcium or 1 oxalate. And we'll divide this by the volume of urine. And then we can take out the milliliters. And this gives us 0.007108 molar calcium plus 2 in the urine.
Yep.
Excellent. Oh my gosh. My fact check came out right. You have no idea how relieved I am. I was thinking about this the whole time through the problem. So, so this is, so this here, it's moles per liter here. So where did my volume go away, right? Because I see mils here cancels mil. And this is a volume times a molarity.
Oh no.
So this is 1 liter. There it is. That's where it goes. That's where it is. So this is moles of permanganate divided by liters. Aha. I forgot the L up here. That was getting me. My dimensional analysis was crumbling as went my confidence in this question. So this is how we would do this, right? Now, let's go back to the PowerPoint tab, and let's see if I got it right. Okay. 7108. They got 7111.
7108 is whenever they do that, it's going to be 711.
I made a mistake somewhere, huh?
No, I mean,
oh no,
it
no.
is 71.
We have a different molarity. Yeah, we have a different. We're differing in these digits. So I have 8.792. They have 8.79. So it's
That's
okay.
correct.
We're
Yeah.
doing this. We're doing it the same way. So this is a small difference. I think I carried this from the previous page, and I must have made a tiny error somewhere where they did. So this comes out to 10711 or 108 or whatever, something like that. Molar, right? Oh, and actually the 5 mil here, this limits at 3 sig figs. This is 3 sig figs. Oops. I think you can see this shit, but you can't really see it. Why do I have it be small, like the corner here? Right? Maybe we can do like a split screen and have something with a little bit of far-field movement. Oh no, this thing won't get smaller. Stupid thing. Oh well. You're right. I forgot about that. But in any case, there's 3 sig figs in the 5 mils. So this makes this 711. 0.00711. Because this 0 is rounded up to 1. You know, I'm not saying the answers are exactly the same, but it's okay. Okay. So, okay. So coming back here now. Okay, so let's test ourselves here. Let's go with 10 mils. Make this bigger. Make it bigger. Of oxalate, which is at 0.01063 molar. And that reacts with 39.17 molar. oops, sorry, milliliters. Okay, MnO4. And the question is going to be to standardize the permanganate. Okay. So we'll just start with 10.00 milliliters, Na2C2O4. Multiply that by 0.01063 moles per liter. Multiply by 2 permanganates, 35 oxalates of C2O4 minus 2. And then multiply this by 1 over 39.17 ml. And let's see how this comes out, right? This is going to come out from milliliters times moles per liter. Okay? So why don't we, instead of moles per liter here, why don't we say millimoles per milliliter, right? That way we can keep them, we don't have to do the 1000 conversion, right? So 10 times this gives us the number of millimoles of oxalic acid. This gives us the number of millimoles of permanganate, and this gives us the number of millimoles per milliliter of permanganate. This guy comes out here to 0.001086 millimoles per milliliter. This is a MnO4 minus, right? And this is equal to the same number of moles per liter. So I'm not trying to do sleight of hand. I just changed the unit here. As you'll notice in the prior calculations, there was multiply by 1,000 and then divide by 1,000 at the end to get back to moles per liter. And I'm just skipping that by using this unit of millimoles per milliliter. So hopefully that helps. And then, so that's how we can standardize that. And then this required 14.44 mils to titrate calcium in a urine sample. And let's see. So that unknown then required 14.44 mils. Find the calcium in the urine. So so what we're going to do here is we'll this word here is urine sample, right? And then we're going to say 14.44 milliliters of MnO4 minus, right? And we're going to multiply that by 0.001086 millimoles of MnO4 minus per milliliter. MnO4 minus, right? Multiply this by 5 oxalates, 5 C2O4 minus 2, 2 M minus. And we're going to multiply this by 1 calcium for 1 oxalate. And then divide this by the sample size, 1 over 5.00 mLs, right? And then let's do the dimensions here. We've got mils of permanganate, millimoles gives us millimoles of permanganate. This gives us millimoles of oxalate. This gives us millimoles of calcium. This gives us millimoles of calcium. And milliliter of urine, basically. So, and this numerically comes out to 0.007837, but it's 3 sig figs now, so it's could be 0.00784 millimoles per milliliter calcium in urine. Yep. So there's that. Now let's go back to the foils. Now so here's an interesting sort of topic. It seems like a weird sort of a segue side topic, kind of a weird thing, right? But I just want to, it's here, right here, smack in the middle of our curriculum. It's the titration of a mixture, right? And what the key to understanding this is understanding the premise here, which is that 1.372 grams of a specimen containing only these two components, only sodium carbonate and sodium bicarbonate. And that, so this is like, if you knew it was this and it was sodium carbonate, then there'd be no reason to do the titration, right? Because you already know the goddamn answer. The only thing you don't know is what the breakdown between sodium carbonate and sodium bicarbonate is. Does that make sense? So there's carbonate and there's bicarbonate. And you know that they add up to 1.372, right? Their masses add to 1.372 grams. And they require 29.11 mils of this 0.07344 molar HCl for complete titration. Now, the trick here is to find the mass of each component, right? Using this titration data, right? So basically, what they're saying is that if you have sodium carbonate and sodium bicarb, a certain number of moles of them that weigh this much, how many moles of each do you have? So let me do this one on the DocuCam, because this will be posted. Hopefully, it will be more helpful, better paced on the DocuCam. On the DocuCam. Any of this shit here. There we go. So in this case, what we have is 2.000 4 sig figs grams of K2CO3 plus KHCO3, and they are both being reacted to make CO2 plus H2O using 28.10 milliliters of 1.000 molar HCl. This guy is 138.20 grams per mole, and this guy is 100.11 grams per mole. Right, and so let's figure out first how many moles of H plus was used in this titration. So that's going to be 28.10 milliliters times 1.000 millimoles per milliliter, right? This is equal to 28.10 millimoles of H plus, right? Now, so 28.10 millimoles of H plus, this here is equal to this is equal to the number of moles of H plus it takes to react with this plus this, right? So let's just say that there's X grams of K2CO3. Then there's 2.000 grams minus X grams of KHCO3. Right, so here's where the trick comes in, right? Is you just set it up this way. So now what we're going to do is we're going to convert these into moles, right? So we're going to say X times, now this is going to be 2 moles of H plus for every 138.2 grams per mole of K2, right? Plus 2.000 minus X times 1 mole of H plus for every 100.11 grams per mole here. Grams per mole. No, grams per mole. Right? This is KHCO3. And this here will equal this. 0.00, no, 0.02810 moles of H plus. All right, that's a little bit messy there. But the trick here is to get these two terms separated out, right? And then you can basically just do the math here. This is 0.01447x plus this term, right? Well, this term here comes out to 0.019978 minus 0.009989x equals 0.00280. And now we can just collect our terms here. This minus this, and then this minus this. Get them all on the same side here. Comes to 0.004481x. 0.008122. X equals 1.812 grams of K2CO3. Then 2 minus X is equal to 0.187 grams of KHCO3. So that's sort of like the slow version of how to do that. So the reason that this is the last digit here is because these come from a subtraction type calculation. This is 4 sig figs. This is carried through the multiplication. And this is 3 sig figs because of the subtraction. So I think, and let's go ahead and start one on the next topic here. I'll just give it a couple minutes here. And this next one is going to be we're basically doing a sort of a gravimetric titration. That's not we're doing a precipitation titration, right? We're taking a silver solution, reacting it with an iodide solution, right? And at this point, let's say that we know both the starting materials. We have 25.00 milliliters of 0.100 molar iodide. And we're going to titrate this with 0.0500 molar Ag plus. And what's going to happen is that the K plus, the Ag plus and the I minus will precipitate to form AgI solid. And the KSP for this is equal to 8.3 times 10 to the minus 17, right? This is going to ultimately limit our precision here. We have high precision numbers, but that's not so precise, right? And what we're asking now is at so at 49.00 milliliters of 0.0500 molar Ag plus, what is the Ag plus ion concentration and the I minus concentration in the flask? So this is an interesting question. It's sort of like leading up to the endpoint. The endpoint is at 50.00 milliliters here, right? So the answer here, I don't quite have time to go over, but what I'm asking you to think about is this case where we have a flask. We've been titrating in Ag plus, right, I think. This has an iodide source, and then we've made a small pile of AgI solid. So what we're asking now is what the Ag concentration is here in the presence of just the amount of iodide that we reacted with up here. So, okay, sorry, I've got to go. Thank you all for your attention, and we'll pick this up on next Tuesday, okay? Any questions?
Thank you, Dr. Terrell. Have a good one.
Thank you, thank you.
Thank you, Professor.
Thanks, Ryan. Thanks, everybody.
Doesn't make sense.
Professor,
Oh, yeah.
what chapter will be on the exam?
What chapters are going to be on the exam? 7 for sure. So, like 5, 6, 7, I think. So I will get back to you that in a notification. Okay. All righty, guys. Thank you very much.